All right, in this lesson we're going to continue adding some of the derivative and integral rules. And so far in this chapter you learned how to differentiate and integrate using exponentials using base e. So we do need to address what do the derivative and integral rules look like for bases other than e. So if we had like 3 to the x or 4 to the x, how would that rule behave differently than the ones that we've already learned? So we're going to begin today with a quick refresher of how do you solve exponential equations. How do you change from bases other than e to base e, or how do logs work with natural logs, just to kind of get you back into that mind frame. And then we're going to use some of those algebra facts to help us in showing where the calculus is going to come from. All right, so just want to get down again some of the basic workings of the relationship between exponentials and logarithms. Just as a quick refresher, recall again that a to the x is equal to y. If we know that that's true, we also know that log base a of y is equal to x. Also, logarithms and exponentials are inverse operations or inverse functions. So log base a of a to the x, the logarithm and the exponential operations cancel out, and you end up just getting x. Similarly, a to the log base a of x is equal to x. So those are some facts that we can use for solving exponential and logarithmic equations. So these equations can be solved using both of those facts, approached from different ways. So if we have the equation 3 to the x equals 1 over 81, some of you might approach solving that in different methods. Some of you might take a look at that and you can actually use mental math to solve that. 3 to the x is equal to 1 over 81. Well, what power of 3 can give us 1 over 81? Well, what power of 3 gives us 81? Well, 3 squared is 9, 3 cubed is 27, and 3 to the fourth is 81. But since the 81 is in the denominator, we would want x to be a negative exponent. So some of you might look at this and go, oh, I know x is negative 4 then. Okay. Another way to look at this, or if this was one that you couldn't do with mental math, is to get the x out of the exponent, you would want to rewrite this as a logarithmic equation. So log base 3 of 1 over 81 is equal to x. Okay, and then you would evaluate log base 3 of 1 over 81, which is also negative 4. And then if you weren't sure what to do this, some of you can plug in bases other than 10, other than just the common logarithm into your calculator, and you could plug that in and you'd get negative 4. In just a second, we'll talk about how to use change of base formula to evaluate this as well if you only can do the common logarithms on your calculator. Okay, so similarly, if I have log base 2 of x is equal to negative 4, to get x out of the inside of that logarithm to be able to isolate x and solve the equation, you'd want to switch from logarithmic form to exponential form. So 2 to the negative 4 power is equal to x, and then you would want to evaluate 2 to the negative 4. So this is something that again can be evaluated using mental math, but if it was something that was not, you'd want to use your calculator to solve that or simplify it. So 2 to the fourth power is 16. So because of the negative power, I'd have 1/16. All right, so then I had just mentioned a second ago that to be able to evaluate logs other than the common logarithm, you might want to remember change of base formula. So how that's defined is log base a of x, so essentially that tells us any logarithm base, that's just what the a stands for. If we want to switch it to natural log, that would equal to natural log of x over natural log of a. So essentially natural log of what was inside here divided by natural log of the old base. Similarly, that's going to equal log of x over log of a. So you can really use this to convert to any log. We commonly work with natural logs in calculus just because we already have derivative and integral rules that apply for base e, but just so that you're aware that you can use it for switching to common log as well. We're going to end up using these properties to help us come up with derivative and integral formulas for bases other than e. All right, so let's just kind of use the properties that we just learned to just review solving some exponential and logarithmic equations just so that you're able to work with them when you need to using maybe first or second derivative test. So if I have 4 to the x plus 3 is equal to 12, to get the x out of the the exponent there, I would want to switch to logarithmic form. So I have log base 4 of 12 is equal to x plus 3. All right, this has a numerical value, so I want to go ahead and evaluate that. This is something that I wouldn't want to use mental math for, because 4 to some integer power, or even something you can use mental math, you're not going to be able to evaluate that. So what I want to do then is switch this using change of base formula. So natural log of 12 divided by natural log of 4 is equal to x plus 3. So then to get x by itself, I would subtract 3, so natural log of 12 over natural log of 4 minus 3. So I'm just going to evaluate that on my calculator just to make sure that we're all on the same page with that. So natural log of 12 divided by natural log of 3, or natural log of 4, pardon me, minus 3. So I get negative 1.207. All right, so then now I have this logarithmic equation here. To be able to solve this, or to get x by itself, I do need to use log properties to combine that into a single logarithm. So since I have a sum here on the interior of my log, that's going to become a product. All right, so then if I want to switch that to exponential form, I have 5 to the 1 power is equal to 2 times quantity x plus 3. Probably want to distribute the 2. 5 to the 1 power is just 5. Okay, so then I subtract 6, so I get negative 1. So x is equal to negative 1/2. So even though you might not be working with something up here that looks like it'll be easy to solve using mental math, it certainly could be the case that you don't even need your calculator to solve. A real common application that goes along with exponential equations is radioactive half-life. So perhaps the half-life of carbon-14 is about 5,715 years. A sample contains 1 gram of carbon. How much will be present after 10,000 years? All right, so if I'm doing half-life, the exponential equation that goes with that is y is equal to 1/2 to the t over 5,715. And the reason, and so there's a 1 here for this 1 gram of carbon, just so that you're aware of that's in the setup. Okay, so after 10,000 years, I would want to go ahead and just plug in 10,000 for t. So 1/2 to the 10,000 divided by 5,715. So 10,000 years is not quite 2 full half-lives. So I would expect there to be, if it had gone through 1 half-life, I would expect there to be 1/2 gram. And if it went through another half-life, I'd expect there to be 1/4 of a gram. Since it's not quite 2 full half-lives, I'd expect there to be around 0.25, but more than that. If I were to plug this into my calculator, I ended up getting 0.297 grams, which based on my estimate is pretty accurate. Okay, so how much of the sample would be left after 5,715 years? Well, that's 1 full half-life, so I would expect there to be 1/2 gram left. And then, so then with this equation, one of the things that you'll be asked to do is just plug in various times. Another thing that they might ask you is, when is there only 1/3 of a gram left? So you'd have to set the equation equal to 1/3. 5,715. All right, so then to be able to get t out of the exponent there, what I would need to do is to I would want to rewrite that as a logarithmic equation. So log base 1/2 of 1/3 is equal to t divided by 5,715. If you have a calculator that allows you to plug in other bases, that's fine. If you don't, you need to know change a base formula either way. But then I would say, okay, so this is going to be natural log of 1/3 divided by natural log of 1/2 It's going to equal t divided by 5,715. Okay, on my calculator, if I do this product, and then I would have to multiply by 5,715. Okay, uh, so we end up getting 9,058.060 years. All right, so hopefully that was a nice quick refresher for you to kind of recall how exponential and logarithmic bases work kind of at an algebra 2 level for solving equations. Um, so you could probably guess that the derivatives of this are going to behave similar to e, but how similar? So if we want to just kind of look at this a little bit on the graphing calculator, specifically if we want to look at the function f of x equals 3 to the x, I've graphed 3 to the x and its derivative on the same viewing window. This is a standard viewing window, negative 10 to 10 here, negative 10 to 10. In blue is 3 to the x. I guess it didn't show up real well here, but this is 3 to the x. And then I've graphed its derivative on the same viewing window, which is showing up in red. So notice down here they look to be about the same, but then up when you get in this region here, they do look very similar, but I can see that the blue and the red are separate, so they aren't exactly the same. So based on that information, I can say that the derivative of 3 to x is not exactly 3 to the x, because recall the derivative of e to the x is e to the x. They do look very close. They must differ by some small factor. And I'm saying a small factor because you can tell that these are almost identical, but not exactly identical. So let's go ahead and show where the derivative of 3 to the x would come from. So what we're going to do is go ahead and start with log base a of x, just to kind of pick one to get going with. So the first thing we're going to do is use change of base formula to get this to something that we know how to use. So I'm going to say natural log of x over natural log of a. Okay? So if I want to go ahead and take the derivative of that, the derivative of natural log of x is 1 over x, and then natural log of a is a constant, so I have natural log of a just hanging out right there. So from here on out, the derivative of log base a of x is equal to 1 over x times 1 over natural log of a. Alright, so we'll use a similar idea and actually go back to the last example and try to look at where the derivative of that comes from. Okay, so if I was looking at 3 to the x, let's go ahead and try to take the derivative of that. Well, since x is up in the numerator there, let's go ahead and switch to logarithmic form and see if we can use some of the information that we just learned. So log base 3 of y is equal to x. Okay, if we want to use change of base formula, natural log of y divided by natural log of x, natural log of 3, pardon me. So let's go ahead and take the derivative of this. So the natural log of y is going to be 1 over y prime by chain rule times 1 over natural log of 3. The derivative of x is just 1. So if I get y prime by itself, which is my goal because I want to take the derivative, I'm going to multiply y to the other side. I'm going to multiply natural log of 3 to the other side, and the 1's just hanging out. So the derivative is equal to y times natural log of 3. And recall that y is equal to 3 to the x. So the derivative is 3 to the x times natural log 3. All right, so if we look at this, oops, the derivative of 3 to the x was 3 to the x times natural log 3. Well, that's pretty close. It's not exactly 3 to the x, but it differs by some factor. So we can go ahead and we can generalize. This is true that the derivative of a to the x will be a to the x multiplied by a factor of natural log a. So those are our two rules for today. Notice that they're alike. Um, they're similar to working with logs and e to the x. So let's go ahead and just practice taking some derivatives and evaluating some integrals. So if I want to take the derivative of 2 to the x, the derivative is just going to be natural log 2 times 2 to the x. Okay, the derivative of y equals 2 to the 3x. This is going to be, again, very similar. Natural log 2 times 2 to the 3x, and then I need to multiply by 3 by chain rule because I did have a composition of functions here. Okay, so if I have y equals log base 10 of cosine of x, so the common log, so the derivative is going to be 1 over natural log 10 times 1 over the inside times the derivative of the inside because of chain rule. So negative, oops, that didn't come out real clear. So times negative sine of x. You're certainly welcome to leave your answers like this. Simplifying is not important at this stage, but if you had wanted to clean it up a little bit, like if you were to see this on a multiple choice situation, sine over cosine's tangent, so you might end up seeing this as like negative tangent divided by natural log 10. I'm certainly not required to rewrite that, but just so you're aware of alternative forms. So if I see y equals log base 2 of x squared minus 1 over x, if you were to just go ahead and take the derivative from right here, when you take the derivative of the inside, that will require a quotient rule. Or some other kind of simplifying. I would recommend using the log properties to expand it first. So log base 2 of x squared minus 1 minus log base 2 of x. So I go ahead and take the derivative, 1 over natural log 2 times 1 over the inside, so 1 over x squared minus 1 times 2x by chain rule. So then the derivative of this part here, 1 over natural log of 2 times 1 over x. Okay, so old rules will start to be used along with some of the new ones that you have. So if you have y equals t squared times 2 to the t, we're going to need to do product rule overall for that. So the derivative, so order not being important in product rule, I usually do the same order as quotient rule just to keep it fresh. So g times the derivative of f, so the derivative of t squared is 2t times 2 to the t. Okay, then fg prime, so t squared, the derivative of 2 to the t is natural log 2 times 2 to the t. Alright, so the integral formula is going to, or taking the antiderivative is going to behave very similarly here. The antiderivative or the integral of a to the x is 1 over natural log a times a to the x plus c. The reason for this being is notice that this is representing a derivative, and the derivative is missing the natural log a there that we would expect it to have, so I need to compensate that by having the reciprocal out front. Okay, so the antiderivative of 2 to the x is going to be 1 over natural log 2 times 2 to the x plus c. Alright, so as before, we're just continuing to add to our toolbox of rules. U substitution is going to be used. Definite integrals will be used. You might even be reviewing some of your left hand, right hand rules and that type of thing, just to keep all of those fresh and knowing that they're applicable to this family of functions as well. So this does require a small u substitution, so u is x over 2. Okay, I don't have a 1/2, so I'm going to have to compensate for that by having a 2 out front. So 4 to the u du. Remember that you can't write the bounds down the same as what they were here, so you're welcome to either switch back to x's at the end or convert your bounds right now. If I have negative 1 in the denominator here, if I go ahead and switch that from x's to u's, I'd have a negative 1/2 on the bottom. Okay, and if I go ahead and plug in 2, I'd end up having a 1 here. All right, so the 2 carries down. I'm going to have 1 over natural log 4 times 4 to the u from negative 1/2 to 1. If I go ahead and plug that in to my calculator, I end up getting approximately 5.049 then to 3 decimal places. Okay, just to kind of wrap up with just a couple of other examples here. So I have u substitution, so u is equal to negative x squared dx. The derivative of that would be negative 2x. I have the x, but not the negative 2, so I have a negative 1/2 out front. 5 to the u du. Okay, so then negative 1/2, 1 over natural log of 5, 5 to the u, which is negative x squared, plus c. Okay, I have another definite integral here. I'm going to be using u substitution again. So u is equal to cosine of x dx. Du is equal to negative sine of x. So I have the sine of x but not the negative, so I'm going to bring the negative out front. So I'm going to have 3 to the u du here. If I go ahead and plug in and convert my bounds from u bounds to x bounds, if I go ahead and I plug in 0, cosine of 0 is 1. Cosine of pi is negative 1. Okay, these bounds are considered improper because I have the larger value on top. So remember, you are allowed to switch bounds. So I'm going to make the bottom negative 1, the top 1, but then that would make this opposite. So notice that there's no negative sign there anymore. 3 to the u du. Okay, so that integrates to 1 over natural log of 3 times 3 to the u from negative 1 to 1. So if you want to see algebraically how that would simplify out here, I have 1 over natural log of 3. 3 to the 1 is 3 minus 3 to the negative 1, which would be 1/3. So if you go ahead and simplify that, you end up getting 2.427. All right, so in this lesson we showed the relationship between exponential functions bases other than e and the logarithms, reviewing solving equations, exponential and logarithmic equations, and then how we differentiate and integrate bases other than e.